In earlier assignments, we developed a lexical analyzer, created a syntax analyzer along with a symbol table, and carried out semantic analysis for a subset of the C language. Now we are progressing to the next stage of the compilation process, which is intermediate code generation. This is the bridge between the high-level language and the target machine code. In this assignment, we will first build an abstract syntax tree during parsing and then traverse this abstract syntax tree to generate tree address code. The compiler uses a two-pass architecture, first pass and second pass. Let's explore the components in the first pass: lexical analysis, parsing and semantic analysis, symbol table construction, abstract syntax tree construction. Then in the second pass, abstract syntax tree traversal and a simple assembly-like representation tree address code generation takes place. The abstract syntax tree is the bridge between the two passes. The second pass uses abstract syntax tree to produce intermediate code, typically in the form of tree address code. This approach separates the concerns of syntax or semantic analysis from code generation, making the compiler more maintainable and extensible. You need to implement an abstract syntax tree for the C subset we have been working with. Your implementation should include a base AST_node class. This class will be the abstract base class for all nodes in your abstract syntax tree in a compiler. It provides a common interface for all abstract syntax tree nodes like expression node, assignment node, etc. Now let's have a look at the breakdowns of the components of this class. This is the destructor, marked virtual to ensure that when you delete a derived class through a pointer to AST_node, the correct destructor is called. This is a pure virtual function making AST_node an abstract class. This function is responsible for generating intermediate code for this AST_node. The first parameter output is a reference to the output stream for the generated code. The second parameter, symbol to temp, maps source variables to temporary registers. The third parameter, temp count, is a counter for generating unique temporary variables. The last parameter, label count, is a counter for generating unique labels. It is useful for control flow constructs like if, while, etc. Your implementation should also include a base class for all expressions. This EXPR_node class is a derived class from AST_node and is meant to represent expression nodes in your abstract syntax tree, such as variable, references, constants, arithmetic operations, functions call, etc. It tracks type information for type checking and conversion. Now let's have a look at the breakdown of the components of this class. The node type variable, whose data type is string and the access modifier is protected, stores the data type like int, float of the expression. As the access modifier is protected, derived classes can access it directly. Now, this is a constructor that initializes node type when an EXPR_node object is created. Lastly, this method returns the type of the expression. It's marked virtual, so subclasses can override if it needed. The const at the end ensures the function does not modify the object. Your implementation should also include a base class for all statements. This is the base class for all statements, which also is a derived class from AST_node. Now let's have a detailed look in all the expression node classes. First, we will look into the var_node class for variable references and array access. It handles both simple variables and array indexing and generates code for variable load and array index computation. Here you have a variable name whose data type is string and a pointer index, both of which access modifier is private. Then you can see the constructor of this class. Then we have the destructor which deletes the memory to avoid a memory leak. Next, we have two utility methods. HasIndex method returns true if index reference is not empty, and getName method returns the name of the variable. Now you have another method, generateIndexCode, which generates code for the index expression. You have to design this method by yourself so that this will generate code to calculate the array index and return the temp variable. You should call the generateCode method for the index expression. When you are scaling the index, remember to scale the index based on the element type. For example, 4 bytes for int and most of other types, and 8 bytes for float or double. Lastly, you have generateCode method, which generates the final code. For array access, generate scaled index code. If it's a simple variable, just load the value or reference. Similarly, you have to design the const node for constants, which represents literals like integers, floats. These generate code for operands, then combine them. You also have to design the binary opnode class, which represents binary operations, where code for the operands are recursively generated and gets combined after that. Then you have to design the unary opnode class, which represents unary operators. It generates code for operand, then applies the operation. After that, there is the assignNode class, which represents assignment operation. It will handle both simple assignments and array assignments, along with maintaining mapping of variables to their latest temporary register. Lastly, you will need to design the funcCallNode class, which represents function cells. This will generate parameter passing and call instruction. Now let's have a detailed look in all the statement node classes. Firstly, you have the expr statement node class, which wraps expressions that are used as statements. Then you have the block node class, which represents compound statements. It contains a list of statements and generates code for each statement in sequence. After that, you have to design ifNode class, which represents conditional statements and generates conditional jumps and levels. This class should handle both if-then and if-then-else statement. Then you have whileNode class, which will represent loops. This class generates conditional evaluation, conditional jumps, and backjump. Also, you have forNode class for for loops, which will generate 3 address code for the for loops. You have a returnNode class, which represents return statement. It generates code to computer return value and return code. Lastly, you have the declareNode class, which represents variable declarations. It generates memory allocation for variables and array. After that, you have to use a funcDeclareNode class, which handles function declarations. It sets up function entry points and handles parameters. You also have a very important class called ProgramNode, which represents the entire program. This class generates code for the entire program. This is the root of the abstract syntax tree. This class contains a list of global declarations and function definitions. You will have to design all the generate code method for these classes. For example, if you want to generate a 3-address code for the if block, then first you have to find out from which production rule of your context-free grammar of your YAP file you are going to pass the information. For example, here you can see that the production rule where statement is the production head and if, L parent, expression, R parent, statement, else, statement is in the production body, where according to your input, the expression is A equals to B, then you have parenthesis, then you have statement A equals to 1, then else, and after that the statement for else is A equals to 0. Now you will need to create an AST node for this. So you will need to create an object of if node class of ast.h file. When you are creating the object, you need to pass condition expression, then statement, and else statement from the YAP file. Now, ast.h file generate code for the condition and branch. Then you will have to generate label and code for the then block. Lastly, generate code for the else block. After completing the ast.h file, you will need to do some work on your tree address code file as well. The tree address code generator is created with the ast root and an output string. The generate method is called, which begins by writing the header comments. So you need to write these comments in your output file. Then call the generate code method on the ast root. The ast root passes the call to each global variable or function. Each node in the ast hierarchy implements its own generate code method. Lastly, write a footer to the output file. This two-pass compiler approach allows for better error handling and enables future optimization between passes.